Good evening. Good evening, everyone. Good evening, Yuvraj. So before we start this lecture, let me announce that in combinatorics, I have uploaded few videos. Total 4 videos I have uploaded. Okay. 3 of those videos are basically revision. Okay. So basically those were from the revision classes we took last year. So those are revision classes. So those 3 videos you can watch. Okay, anytime you can watch. Okay, maybe on 2x or maybe on 1.5 speed you can watch. Okay, and one lecture, pigeonhole principle and application of generating function. This lecture, okay, application of generating function and also pigeonhole principle. This lecture I have uploaded. Pigeonhole principle is important, so you can watch that lecture. And this generative function applications are not important. We have already seen what is generative function. We have already solved all the questions of generative function from GATE and TIFR. But one lecture on applications of generative function, just to give you idea why generative functions are important, just to give you idea from where this x is coming, from where that variable is coming. Okay, so this is just to give you the idea. For your curiosity, you can watch that video. Okay, so application of generative function is not important. You can watch the video, and if you understand, that is very good. If you do not understand, don't worry about it, because anyway it is optional. Okay, now let's start graph theory. And those 4 lectures you can watch anytime. Okay, you can watch them anytime. Now Alok is asking, in subgraph we can delete all edge and vertex. Alok, we should have at least one vertex. Whatever graph you have, we should definitely have at least one vertex. Okay, because every graph, whatever graph you have, every graph should have at least one vertex. Is it clear, Alok? We have already seen this in the last class. I told you that every graph must have at least one vertex. So when you say empty graph, when you say this null graph, empty graph, edgeless graph, that is basically a graph without edges. There is no graph without vertices. Every graph must have at least one vertex. But you can have graph without edges, in which all the vertices are isolated. That graph is called edgeless graph. We have already seen edgeless graph on n vertices. Okay, now subgraph can be Arpan. We have 2 type of subgraph. One is induced subgraph, another is spanning subgraph. There are subgraph which are neither of them. There are subgraph which are both of them, and there are subgraph which are one of them and not the other. Okay, by default subgraph means subgraph. Subgraph because subgraph does not need to be induced or spanning. Yes or no? Subgraph does not need to be induced or spanning. For example, if you take this graph, let me take this graph G. I am giving you a graph G, A, B, C. Now in this graph, if you notice, from this graph, let me create a graph like this. Okay, let me create a graph like this. Tell me this graph H. What is this H? This is a subgraph. Yes, H is a subgraph of G. You can notice H is a subgraph of G, but H is neither induced. This is neither induced nor spanning. This is neither induced nor spanning. This is not a spanning subgraph. This is not a induced subgraph. Okay, neither induced nor spanning subgraph. So very simple. Is this clear? Is this doubt? So a graph you have, and this graph H, this is a subgraph. H is a subgraph. I can say H is a subgraph of G, because you are deleting vertices, you are deleting edges, but you are not deleting, you are not adding anything. So you can notice in this H, the vertex set is a subset of G and the edge set is subset of G. So that is the reason I can say this is a subgraph of G, because the vertex set is also subset of G and the edge set is also subset of G. Now let's solve this question. Tell me the answer for this. So try this question. What will be the answer? So the question is asking how many different labeled undirected graphs you have. How many different labeled? Okay, so the question is asking how many different labeled undirected graphs you have. No self loop, no parallel edges, means simple graphs. Okay, on n vertices. So there are n vertices. Already you have n vertices like a1, a2, an. So there are total there are n vertices. Okay. Now the question is saying that you must have labeled. So yes, all the vertices are labeled. Now tell me, already you have n vertices. Now for every edge, we have how many choices? See, you want to create a graph. You want to create an undirected graph. For every pair of vertices, basically I can say for every pair of vertices, you have two choices. Either you can put an edge or you do not put an edge. Yes or no? For every possible edge, you have two choices. For every pair of vertices, you have two choices. Either you make them adjacent or you don't make them adjacent. Yes or no? Only this is what we have. So I can say that for every distinct pair of vertices, for every distinct pair of vertices, we have two choices. We have two choices. What are those two choices? Either you put edge between them or you don't put edge between them. So what are the two choices? Put edge, or don't put edge. Yes or no? So either you put edge between them or you don't put edge between them, because you already have n vertices. So there are n vertices. Now for every two vertices, if I take these two vertices, I have two choices. Either I make them adjacent or I don't make them adjacent. Either I put this edge or I don't put this edge. So for every pair of vertices, we have, for every distinct pair of vertices, these are the two choices we have. So finally, number of graphs. How many graphs you can create? Finally, number of graphs. Remember, for every edge, like this is a possible edge. Either this will exist or this will not exist. Either this will exist or this will not exist. Either this will exist or this will not exist. So for every possible edge, there are two choices. Either it will exist or it will not exist. So answer will be 2 power nc2. Yes or no? Answer will be 2 power nc2, because for everything you have two choices. Is this clear? Anyone has any doubt in this? So for example, if you have, like, for example, if you have n equal to 3, if you have n equal to 3, then total 3 vertices you have. 1, 2, 3. There are total 3 vertices. So how many graph you can create? See, either you can create this graph, or what you can do, either you can create this graph, or you can create this graph, or you can create this graph. Labeled graph we want. So we only want labeled graph. Then, or what you can do, you can create, for example, maybe this graph you can create 1, 2, 3, or maybe you can create this graph, and so on. So like this. So basically, remember, for every pair of vertices, if you take this pair of vertex, or if you take this pair of vertex, or if you take this pair of vertex, for every possible pair of vertex, we have two choices. So either you can make them adjacent or you don't make them adjacent. For example, this is another graph. This is another possible graph. In this graph, see, there are 3 edges possible. Actually, these are the 3 edges possible. So maximum, how many edges are possible? So only 3 edges are possible. For each edge, we have two choices. Either you take that edge or you don't take that edge. Yes or no? Either you put that edge in the graph or you don't put that edge in the graph. So for n equal to 3, what is the maximum number of edges possible? If I ask you, what is the maximum number of edges possible? Maximum number of edges possible. What is that? For every pair of vertices, like for every pair of vertices, you can put one edge, correct? For every pair of vertices, you can put one edge. This is the maximum number of edges possible. Whatever pair of vertices you take, you can take any pair of vertices, okay? And for every pair of vertices, you can put one edge. So these many maximum, these many edges are possible. Now for every edge, we have two choices. Either you can put that edge or you don't put that edge. For example, this is another graph that is possible. Like this, many graphs are possible. So finally answer will be, remember, there are total 3 edges possible. Maximum there are 3 edges possible. You can notice. Maximum there are 3 edges possible. Either you can take them. For this we have two choices. Either you can put it in the graph or you don't put it in the graph. For this, we have two choices: put it in the graph or don't put it in the graph. Similarly, for this also two choices. So the answer will be 2 into 2 into 2, that is 2 power 8, 2 power 3. So this is the idea. So I can say these are the maximum number of edges possible. And for every edge, we have two choices. Either you can put it in the graph or you don't put it in the graph. So the answer will be 2 power NC2. Is this clear to everyone? Tell me. Is this answer clear? That for every everything, for every pair of vertices, we have two choices. So maximum number of graphs. So I can say if you have n vertices, then maximum number of edges. What is that? Maximum number of edges. If you have n vertices, undirected graph, you have n vertices simple graph. I am talking about simple graph. So if you have n vertices simple graph, then maximum number of edges, that will be NC2. Between every pair of vertices, you can put one edge, that is nn minus 1 by 2. This will happen for complete graph. This is the number of edges in complete graph. And what are the maximum number of graphs possible? Maximum number of basically number of simple graphs possible. I can say number of simple graphs. How many simple graphs you can create? Okay, how many simple graphs you can create? So that will be 2 power NC2, because these are the edges, and for every edge you have two choices. Either you can take it or you don't take it. For every edge, already you have n vertices. There are total n vertices already, so that you cannot change. Already we have n vertices. Now let's see the next topic, that is graph isomorphism. What is the definition of graph isomorphism? This isomorphism, remember this word in any field. Okay, whether you study physics, chemistry, mathematics, whatever you study, that is your choice. Whatever you study, this isomorphism, this word will always mean that basically they are almost same, means same structure. Isomorphism means same structure. Okay, whatever you study, whatever field you study, this isomorphism means same structure. This iso means same. This iso means same, and this morphism means form. This morphism means form. Iso means same and morphism means form. So basically same form. So I can say, what is the definition of graph isomorphism? That is the same graphs. If you watch in the abstract view, the graphs are same. The graphs are same in abstract view. Abstract view means, okay, basically if you remove the labels and all. For example, if I give you these two graphs, like for example A, B, C, this graph and this graph, 1, 2, 3, are they same? Can you notice? These graphs are actually same. Why these are same? Because they are abstract view. If you notice their abstract view, they are actually same. If you notice their abstract view, they are actually same. So these two graphs are actually same. If you notice their abstract view. Now similarly, okay, A, B, C, D, this graph and A, C, D, B. Tell me, are these two graphs isomorphic? Like for example, can I say they are basically same? They are basically same. I told you that drawing does not matter. Drawing does not matter. In a graph, drawing does not matter. Basically, they are same, because ultimately, what is this? Ultimately, what is this? If you take this B, pull this B, okay, here, what you do? You pull this B here. You just pull it. Okay. So if you pull this B, then what will happen? It's like this. See, it's like this. You take this B, okay, you pick this B, and what you do? You pull this on this side. Then finally, ultimately, you will get this graph. So yes, these two graphs are also isomorphic. So they have the same form. So same graph in abstract view, or I can say they have the same form. Very simple. Is this clear? It does not matter. Label does not matter. See, this label and all these things does not matter. Basically, these graphs have the same form. Yes or no? Is it clear? This is just twisted. I can say this is just a twisted version of this graph. I can say this is just a twisted version of this graph. This is your G, this is twisted G. So basically both are same. Now let's see some example. For example, This is a meme you can notice. So these two graphs, this is a popular meme nowadays. Maybe you have seen this, right? Okay. So find the difference between these two graphs. Corporate needs you to find the difference between these two pictures. They are the same pictures because ultimately they have the same thing. If you notice, the design does not matter. They are basically the same. For example, these are the isomorphic graph. This is the G and this is the twisted G. This graph is your G and this graph is your twisted G. Yes or no? So this is the simple, this is your basically I can say this is your isomorphism. If you say this is G, then this will be twisted G. Okay, so that is the idea. Next, so basically this is the meme for graph isomorphism. Okay, next. Okay, so if you want to share it someday, then maybe okay, I can put this Go classes here just for credit, just for publicity. Okay, so maybe you can share it. Okay, now let's see. So this is your graph isomorphism. This is your graph isomorphism, right? Okay, so basically this is your graph isomorphism. This is called marketing. Okay, next. So is this graph isomorphism? Is this graph isomorphism? Please say no. Please say no. Okay, so this is not graph isomorphism, but anyway, now let's move on. So let's see. So what is a graph isomorphism? These two graphs, if you notice, then these two are basically, they are basically same. So what does not matter? What does not matter? The labeling does not matter. See, the labeling does not matter. The label does not matter. Correct? Are these two graphs same? Can I say these two graphs are basically same? No. Because in this graph you have a vertex of degree 3. In this graph you don't have a vertex of degree 3. So they are basically different. Actually, they are isomorphic, but these are not isomorphic. These two graphs are not isomorphic. They are very different from each other. This is a path graph. This is not a path graph. Yes or no? This is your P4. This is not a P4. Correct? So this is the idea. So these are not isomorphic. So in a graph isomorphism, what does not matter? What does not matter? In graph isomorphism, what that means basically? Graph isomorphism, what is the idea behind graph isomorphism? Idea is very simple. Idea is like this, that labeling does not matter, first of all. Okay, so this labeling doesn't matter. This labeling doesn't matter. So what you label, that doesn't matter. And also what doesn't matter? So this labeling doesn't matter in graph isomorphism. Also the design, the drawing does not matter. How you draw, that does not matter. How you draw, that does not matter. Okay, so whether you do twist, okay, twist does not matter. So these things basically, these things do not matter in graph isomorphism, all these things. So shape, yes, so the shape does not matter. The shape does not matter. All these things, they do not matter. Okay, ultimately what matters, there are many things that matter basically. For example, the degree sequence should be same. There are many things that should be same. Okay, so now let's see the formal definition. See, for example, if I give you this graph AB and if I give you this graph AB, are they isomorphic? These two graphs G1, G2, are they isomorphic? These two graphs are not isomorphic, because you can notice that in this graph, this is a path graph, this is an empty graph. So these are very different graphs. Yes or no? So these are not isomorphic. These two graphs are not isomorphic. What about these graphs? A, B, C, D. Okay, what about this graph and this graph? Are these two graphs isomorphic? Are these two graphs isomorphic? No. This is your K4. This is not K4. This is not a complete graph on 4 vertices. This is complete graph on 4 vertices. But tell me, are they isomorphic? They look very different. Yes or no? They look very different, but are they isomorphic? Are these two graphs isomorphic? They look very different, but are these two graphs isomorphic? Yes, they are isomorphic, because this is also K4, this is also K4. This is also complete graph on 4 vertices. This is also complete graph on 4 vertices. In this also, every vertex is adjacent to every other vertex. In this also, every vertex is adjacent to every other vertex. So both are basically K4. Ultimately, the design does not matter. The drawing does not matter. The design does not matter. Okay, these things do not matter. But ultimately, they are K4. This is also K4. This is also K4. These two are same. Now let's see one more example. For example, I can say this Q, this graph, this is your, which graph is this? Can anyone tell me which graph is this? This graph is your Q3. This is your Q3 graph. Okay. Now, are these two graphs isomorphic? These two graphs, are they isomorphic? These two graphs. Yes, they are isomorphic. They look very different. They look very different. This is a 3D picture. This is a 3D picture. This is a 3D drawing, I can say. This is a 3D drawing. And this is a 2D drawing. This is a 2D drawing. And that was a 3D drawing. But anyway, they are basically same. Everything is same. This is also Q3. So this Q3 you can draw like this, or this Q3 you can draw like this. Basically, they are basically Q3. Okay. So very simple. Now, actually, this is the 2D representation. Alok, if you notice, they are basically the 2D. This is the 2D representation, because you can notice that very simple. I'm not crossing anything. See, I'm not crossing anything. There is no edge I am crossing. Anyway, we will come back to this. There is a chapter called planar graph. There is a chapter planar graph. There we will discuss this. Again, we will discuss. But anyway, they are basically same. These two. Okay, clear? Now let's see. Now let's see the formal definition. What is the formal definition? What is the formal definition? Because so far we have seen informal definition, but what is the formal definition? First, you understand the idea behind the formal definition. Okay, so let's understand the idea. Have you seen a movie? For example, many times Bollywood movies are basically copy of South movies. Okay, so for example, if you have a in South, there is a movie in South. This is actually my favorite movie, so I am just taking its example. There is a South movie Drishyam of Mohanlal. Drishyam. This is a brilliant movie. You can watch it. This is very nice movie. Okay, Drishyam Part 2. So now, anyway, so there is a movie Drishyam, and there is a sequel of it in the Bollywood that is also Drishyam. Like, I don't know what is the name in the South language. I don't know the name, whether the name is Drishyam or not. I don't know. But what I'm saying that there is a South movie Drishyam and there is a Bollywood movie Drishyam. Okay. Now, in this movie, actually, can I say they are isomorphic? Just think about it. Can I say they are similar? These two movies, how can I say they are similar? These two movies are similar. How can you say these are similar? These are similar because just think about it. Just think about it. This character, can I say this character has a corresponding character here? Tell me, can I say this character has a corresponding character here? Who is the corresponding character? Can I say Tabu is the corresponding character? Can I say Tabu? No, Tabu is not the corresponding character. The corresponding character is Ajay Devgan. Okay. So next, so this, okay, in the South India, you have this actor. In this movie, this vertex, basically, it's like this. Remember, this vertex has a corresponding vertex here. So remember, this is your vertex. This is a vertex, and this has a corresponding vertex here. Similarly, this heroine, what is the actress name? I don't know. I forgot. Can anyone tell me what is the actress name? Who is the wife of Mohanlal? Who is the wife of Mohanlal in that movie? Shreya Sarani is in the Bollywood. Who is the wife of Mohanlal? Okay, anyway. So anyway, forget about it. So she is basically Mohanlal's wife. Okay, so she is basically wife, let me call it. Okay, so she has a corresponding character here. C also has a corresponding character here. So C is a vertex, and this vertex has a corresponding vertex here, and that corresponding vertex is 3A. Okay, next. So there is a police, there is a female police inspector, there is a female uh, there is a female police lead, and she has a corresponding this vertex. Remember, this is a vertex. In this graph, this is your graph. Remember, this is your graph. Okay, this is your graph. Now what I'm saying that in this graph, this vertex has a corresponding vertex here, and that vertex is tabu. Okay, so like this, and so on. Okay, and so on. So basically every vertex has a corresponding vertex here. Correct? Yes or no? Very simple. So this is the idea, that these two movies are isomorphic because this graph and this graph are isomorphic because there is a correspondence. There is a correspondence between the vertices of this graph and vertices of this graph. There is a correspondence. There is a bijection. There is a one-to-one bijection. Yes or no? There is a one-to-one correspondence between these vertices and these vertices. There is at least one bijection, such that what should happen? Is this enough? Just think about it. Is this enough? Is this enough? This is not enough. What is enough? See, if they have dialogue, if they have some dialogue, then they should also have a dialogue, similar dialogue. Yes or no? If they have dialogue, then they should also have a dialogue. Agree or not? For example, that popular dialogue, that 2nd October dialogue. Do you remember the 2nd October? Where was Ajay Devgan and his family on 2nd October? So that story, that dialogue is here also, here also. If some dialogue is here, if you have some dialogue here, then that dialogue, that same dialogue should be here also. And if there is no dialogue, just think about it. If there is no dialogue between these two, if there is no dialogue between these two, then there should be no dialogue between these two. Yes or no? Because this corresponds to this and this corresponds to this. So if they do not have any dialogue in this movie, then they should not have any dialogue in this movie. I hope this example is clear. This is just the idea, like, okay, just to explain the idea of isomorphism. And this is your isomorphism. This is the definition of isomorphism. So when can you say that two graphs are isomorphic? You have a graph G, V, E, and you have a graph H, which is V2, E2, which is V2, E2. This is your graph V1, E1, and this is graph V2, E2. Then what is the definition of, see, G is isomorphic to H if and only if there exists. Please notice this. Please understand the definition, because I tell many times this point. I tell many times that anyone who understands the definition, you have already cracked the GATE exam. If you understand the definition, I give you some definition, you think about that definition. If you understand that definition carefully, then you have cracked the GATE exam. I guarantee you that. Because many people, they do not even try to understand the definition in front of them. So just understand the definition, you will understand everything. So G is isomorphic to H if and only if there exists, this is important, there exists a bijection. There exists a bijection between V1, V2. Okay, means these vertices and these vertices. This is a movie, this is a movie. There should exist a bijection between the characters. Yes or no? Agree or not? So what I am saying, that in this movie, if you notice in this movie analogy, what is happening in this movie analogy? This is happening that this Drishyam South is what? In this analogy, tell me, this Drishyam South is what? This is the graph. Yes or no? And this Drishyam South, Drishyam Bollywood, what is that? That is a graph. So in this analogy, basically, in this analogy, this is your graph G. This is basically your graph G, V1, E1. And this is basically your graph. This is basically your graph H. This is your graph H, V2, E2. Okay. So you have two graphs, V1, E1. Correct. So in this analogy, the movie is basically the graph. Okay. And the characters are what? Tell me, the characters are what? the characters are what? The characters here are the V1 and the characters here are the V2. Here the characters are V1, the vertices are the characters. These are the characters. Okay, and dialogue between two people. And dialogue, if you have some dialogue between A, comma B, dialogue between A, comma B, that is basically age between A, comma B. That is basically age between A, comma B. Yes or no? So the dialogue between two people, that is basically the age between two people. Okay. And if there is no dialogue between two people, then there is no age between two people. So this is the movie analogy. In this movie analogy, you can understand that when can I say that these two movies are isomorphic? I can say two movies are isomorphic. Tell me, when will you say two movies isomorphic? Isomorphic. If and only if there must be a bijection between the characters. Correct? There must be bijection between the characters. You must have a bijection between the characters. So there must be a bijection between there must exist a bijection between the characters. You must have a bijection between the characters. This bijection should preserve, remember, this bijection should preserve dialogues. Should preserve dialogues. This should preserve dialogue. What it means? This should preserve dialogue. What this means? This means that if there is a dialogue between A, comma B here, then there should be a dialogue between FA, comma FB here. And if there is no dialogue between C, comma D here, if there is no dialogue between C, comma D here, then there should be no dialogue between FC, comma FD here. Yes or no? Is it clear to everyone? So the two movies are isomorphic. When can I say two movies are isomorphic? When their characters, you can put their characters in one-to-one correspondence. These are the characters, Mohanlal wife, this female police officer, okay, and these are the characters here. So when you can put the characters in a one-to-one correspondence, such that, this is important, such that the dialogues must be preserved. Means if these two people have a dialogue, then their images also should have a dialogue. If these two people have a dialogue, their corresponding character here also must have a dialogue. If these two people don't have a dialogue, then their corresponding character must also not have a dialogue. This is the definition of isomorphism. So isomorphism definition says that two graphs are isomorphic if and only if there exists a bijection between V1 and V2 which preserves edges. Which preserves edges. What it means? It means that A, comma B, okay, it means that A, comma B, they belong to V1. Okay, so A, comma B belong to E1 if and only if they belong to E1, if and only if their corresponding, their images, their corresponding characters, they belong to E2. Yes or no? So they should preserve edges. Means A, comma B, they have age if and only if their images also have age. And if they don't have age, then their images also don't have age. So they should preserve edges. The definition of isomorphism, is it clear to everyone? Please tell me. Is the definition clear? Because in the GATE exam, they can ask you the definition also. There is a question, there is a very, very, very nice question in the NET exam. In that question, they are asking definition of graph isomorphism. Okay, and what they will do in that definition, what variation they will do? This type of variation they will do in that definition. This type of variation they will do. Manideep, this is the set of edges. E1 is the set of edges. Means A, comma B, there is age between A, comma B if and only if there is age between, this is the idea. A, comma B, there is age between A, comma B if and only if there is age between their corresponding characters in the other graph. This is the idea. Okay. So let's understand this by example. So why these two graphs? For example, A, B, C. This graph, let's call it G. Okay, and let me give you another graph. 1, 2, 3. So why these two graphs are isomorphic? What can you say? What is the reason they are isomorphic? Tell me. Prove they are isomorphic. Prove they are isomorphic. So how will you prove they are isomorphic? To prove that they are isomorphic, if you want to prove that they are isomorphic, to prove what you have to do, if you want to prove they are isomorphic, what you have to do, you have to give one-to-one correspondence. You have to give one-to-one correspondence. You have to give a bijection between these vertices. You have to give a bijection between these vertices. At least one bijection you have to give, which preserves the edges. Which will preserve the edges. So can anyone give me a bijection which will preserve the edges? Tell me, will this bijection work? Let me give you a bijection. Give him a, will this bijection work? Will this bijection work? This bijection, will it work? This bijection will not work. This bijection will not work. Why this bijection will not work? Why this bijection will not work? See, this is a bijection that is fine. Bijection is fine. Remember, bijection is fine. You must have a bijection between V1, V2, which preserves the edges. Which preserves the edges. This is very important. Which preserves the edges. What it means? What it means? It means that if they have dialogue, then they should also have a dialogue. Yes or no? See, this bijection will not work. Arpan, please see this. Do they have a dialogue? Tell me, these two characters, do they have a dialogue in this graph? In this graph G, these are the graph G and these are the people of H. Do they have dialogue between these two? A, B. Yes, they have dialogue, right? So yes, they have dialogue. Now they also should have a dialogue. Do they have a dialogue? Do they have a dialogue? Means they have an age. These two people have age, but their images don't have age. Their images don't have age. Yes or no? So ages are not preserved. See, AB has age. Now you can notice that one thing you notice, AB belongs to E1. AB belongs to E of G. But F of A, comma F of B does not belong to E of H. So you can notice A, comma B, they have dialogue between them, but their corresponding characters don't have dialogue. So this bijection will definitely not work. So can I say they are not isomorphic? This bijection will not work. So can I say they are not isomorphic? No, because remember there exists a bijection. This is the important point. There exists a bijection. There exists a bijection. If this bijection is not working, try something else. If this bijection is not working, try something else. Okay, so let me try. Let me try. Let's see, will this bijection work? So let me do this bijection. Will this bijection work? Please tell me. Will it work? This bijection will also not work. This bijection will also not work because 2, 3, they have dialogue. 2, 3, they have dialogue. A, B also have dialogue. That is fine. Very good. There is no problem. But why this bijection will not work? Why? What is the reason this bijection will not work? This bijection will not work because they have dialogue, right? See, if you notice, these two people, they don't have dialogue. B, C, they don't have age. B, C, they don't have age. They don't have age. But 3, 1, they have age. So this bijection will also not work because this bijection is not preserving edges. You can notice B, C does not belong to E of G. B, C does not belong to E of G, but F of B, F of C, that belongs to E of H. So I can say yes or no. So this bijection will also not preserve the edges. The edges are not preserved. So what to do? So can I say this is not isomorphic? How many bijections we have to check? Can anyone tell me? Please tell me. How many bijections are there? We have to check. How many bijections? Total 6 bijections are possible. Total 6 bijections are actually possible. If you notice, there are total 6 bijections possible. 3 factorial. Number of bijection possible is 3 factorial. So total 6 bijections we have to check. One of them should work. Remember, total 3 factorial bijections we have, but we only care about one bijection. We don't care about these bijections. We only care about one bijection. So which bijection will work? You can check this bijection will work. ABC 3, 1, 2. You can check this bijection will work. This bijection will work. This bijection will also work. Remember, this bijection will also work. So that is the reason there exists. This will also work. So 4 bijections will not work, but 2 bijections will work. Yes or no? Is it clear to everyone? See, these 2 bijections are not working, but these 2 bijections are working. And we only want one bijection. This bijection is working. Why? See, notice that A, B, they have age. 3, 1, they also have age. A, C, they have age. 3, 2 also have age. B, C don't have age. 1, 2 don't have age. So everything is working. Yes or no? See here. Check it here. A, B have age. 3, 2 have age. Next, B, C don't have age. 2, 1 don't have age. So everything is working. So ages are preserved. So this bijection will also work. This bijection will also work. And we only want one bijection. There exists a bijection which preserve the edges. So you can notice this bijection will preserve the edges, and this bijection will also preserve the edges. So finally, I can say they are isomorphic. Is this clear to everyone? Please tell me, is this clear? So first of all, remember, okay, this is the idea. Now let's see another question. These two graphs, A, B, C, and this graph, A, B, C, this graph, are they isomorphic? Prove they are not isomorphic. Prove they are not isomorphic. How will you prove they are not isomorphic? How will you prove they are not isomorphic? What you have to do if you want to prove they are not isomorphic? What you have to do? What you have to do to prove that they are not isomorphic? No bijection will work. Now you can notice no bijection will work. Whatever bijection you create, that will not work. So basically no bijection. Total 3, see, there are total 3 factorial bijections are there. We have total 3 factorial bijections. This is your G, this is your H. 3 factorial bijections between vertices of G, vertices of H. But none of them will preserve edges. None of them will preserve dialogues, will preserve dialogues, or will preserve edges. So none of them will preserve edges. Whatever you do, very simple. There is a bijection. Don't say there is no bijection. There are 3 factorial bijection we have. So bijections we have between VG, VH. We have total these many bijections we have. We have bijections, but they don't preserve edges. Whatever bijection you create, that will not preserve edges. See, they will not preserve edges. For example, if you take this bijection, let's assume that you take this bijection ABC, ABC. Now let's assume you take this bijection. Will it preserve edges? Let's assume you take this bijection. So tell me, for example, let me give you this bijection. Will it preserve edges? This bijection is not preserving edges because you can notice there is no edge. There is no edge between B, C in G. In G, this is your G. In G, there is no edge between B, C. But there is edge between C, A. Between C, A, there is edge in H. In H you have. So whatever bijection you create, that will not, so these many bijections we have, but none of them will preserve edges. Tell me how many bijections you have from set this is my question. Okay, number of bijections. Number of bijections. Number of bijections. How many bijections you have? Tell me. For example, if you have a if you have set A whose cardinality is 3 and there is a set B whose cardinality is 2, how many bijections you have? So number of bijections. Tell me. Number of bijections from A to B. Okay, from A to B, number of bijections between A comma B. How many bijections you have? So tell me. The bijection, that will be 0, because these are two. Okay, I told you that bijection exists if and only if they have same set, they have same cardinality. Bijection A to B exists. Bijection exists. I told you this point. Bijection exists if and only if their cardinality is same. If and only if their cardinality is same. Because they have different cardinality, so bijection is not even exist. So number of bijection will be 0. Number of bijection will be 0. Now let's assume you have 3 here, 3 here. Now how many bijections you have? How many bijections you have? What is the number of bijections? So number of bijections from A to B. From A to B. How many bijections you have from A to B? So remember, these are the bijections. If you notice, what you do, fix A. See, this A you fix. This A you fix. A, B, C, this you fix. This B, 1, 2, 3. So this bijection is created. I can create this bijection, 1-to-1 correspondence. I can create this bijection. Fix A. Don't change A. Don't change A. Now you can rotate this in how many ways? This, how many ways you can rotate? 3 factorial ways. You can rotate in 3 factorial ways. This is another bijection. Fix A. Don't change A. Don't change A. Don't change A. Don't change A. This is another bijection. Don't change A. Fix A. So just fix A. Then what you do? Fix A. This is another bijection. Similarly, fix A. Don't change A, but you can rotate B. So this B you can rotate. 3, 1, 2. This is another bijection. And finally, this is another bijection. A, B, C. Fix this A, and now 3, 2, 1. This is another bijection. Can I create something else? Tell me, please tell me. Can I create another bijection? Like, can I create this bijection? Anything else can I create? Only 6 bijection I can create. Yes or no? This bijection, can I, like, for example, can I say this bijection? Did I cover this bijection? Like A, B, C. Did I cover this bijection? Just tell me this point. A, B, C, 1, 2, 3. This bijection did I cover? Did I cover this bijection? Please tell me. Where did I cover this bijection? This bijection, where did I cover? Which one? These two are same. This and this, they are actually same. The third one, they are actually same. This one and this one, they are actually same. So you can notice, yes, this is also covered. Remember, this bijection is same as this bijection. Both are actually same. They are actually same. There is no difference. They are actually same. So only how many bijections you have? So finally, number of bijections. This is the idea. Number of bijections. Okay. From A to B, where cardinality of A, cardinality of B is equal to n. So how many bijections will be there from set A to set B? Number of bijection. Very simple. Fix A. This A you don't change. Don't change A, but permutation of B you can do. What you can do? You can just do like this. Now what you do? You do permutations of B. So here you can put any permutation of B. Any permutation of B you can put. Okay. Fix this. This is fixed. Fix this. Okay. This is fixed. So this order is fixed. This order is fixed. Now what I can do? Now I can put permutations of B here, and okay, these are, so finally I will get bijections. So how many bijections are possible? Number of bijections, what that will be? Number of bijections, that will be n factorial. These many bijections will be there. Very simple. Okay. So finally here, remember, in this case, now you can notice that 3 factorial bijections are possible because vertices of G, there are 3 vertices here, there are 3 vertices here. So between these vertices and these vertices, there are 3 factorial. There are 6 bijections possible, but none of them will preserve edges. None of them will preserve edges. Is it clear to everyone? Please tell me. Tell me, is it clear? This is the definition, Manisha. That is the definition. Why do you question definitions? Many times I have seen, like, you were questioning the definition of generative function. You are questioning definition of isomorphism. Don't question the definition. All the edges must be preserved. Every single edge must be preserved. If something is not preserved, then cancel. Everything must be preserved. For all this should happen. Okay. So remember, finally, this is the conclusion. Please understand, this is the conclusion of this definition. We will not apply this definition. Let me tell you. This definition, can you notice? It will take a lot of time if you apply this definition to check isomorphic. So this is the conclusion of definition. So the definition of isomorphism, and this is the conclusion. What is the definition of isomorphism? Very simple, that you have a graph G in which you have V1 comma E1. This is the graph G, and you have a graph H V2 comma E2. Then G is isomorphic to H if and only if there exists a bijection between V1, okay, between V1 to V2. There exists a bijection from V1 to V2 such that there exists a bijection F. There exists a bijection F from V1 to V2 such that, okay, what? So I can say, so there exists a bijection from V1 to V2. There exists a bijection F such that if this edge, okay, if this edge belongs to E1, if and only if this FA comma FB, means their corresponding vertices. If these two have edge, then their corresponding vertices should have edge. If these two don't have edge, their corresponding vertices should not have edge. Is this clear? And this should happen for all. This should happen for all. This should happen for all A comma B. This should happen. So this should happen for all A comma B, that if they have edge, then their corresponding, then their images also should have edge. If they don't have edge, then their images also should not have edge. So they have edge if and only if they have edge. This is the definition of isomorphism. But this isomorphism, if you apply, for example, let's assume I give you a graph. This is my question. Let's assume you have a graph G, 10 vertices. Okay, you have a graph G with 10 vertices. You have a graph H with 10 vertices. How much time it will take to prove? Okay, if you apply definition to check isomorphism, if you apply definition, then how much time it will take to check isomorphism? If you apply definition, then how much time it will take? Then you have to check 10 factorial bijections. You have to check. First of all, 10 factorial bijections need to check. We have to check 10 factorial bijections. These many bijections we will have to check. If you have 10 vertices, these many bijections, and this is a very, very huge value. This value is very big. Okay. So that is the reason we will never apply the definition of isomorphism. The definition of isomorphism we will never apply. Never. This definition I told you because in the NET exam, NET, in the NET exam, there is a question in which they are asking, directly they are asking definition. There are 4 options, and in those 4 options, they are asking the definition of isomorphism. So in the GATE exam also they can do this, because in the GATE examiner knows, the GATE people know that students can find isomorphic. Like if I give you 2 graphs, you can find whether they are isomorphic or not. Many people can do that, but many people don't understand the definition of isomorphism. So in the GATE exam, they can give you 4 options, and one of them will be the definition of isomorphism. Other things will not be the definition. Like they can change. For example, they can change something. Okay, in one option they will give you this definition. In another option they will create for all. Okay, in another option they will remove this if and only if, and they will create if. See, in another option they will do this. So basically, this type of thing they can do. They can do whatever they want. Okay, so these are the ideas. Anyway, so remember, we will never apply the definition of isomorphism to check whether the graph are isomorphic or not. So what we are going to do? Let me tell you few things. So never apply isomorphism definition. Never apply isomorphism definition to check isomorphism, to check if two graphs are isomorphic. Okay, to check if two graphs are isomorphic. Never apply this definition. So now what we are going to do? Actually, proving that two graphs are isomorphic is very hard. Let me tell you. First of all, let me tell you that if you want to prove, okay, proving that two graphs are isomorphic is very hard. Proving graph isomorphism, if you want to prove that two graphs are isomorphic, then this problem, if you notice, this problem is a very hard problem. This problem is very hard. This problem is known as NP. There is a word for it, that is NP intermediate problem. This is a NP intermediate problem. What it means? NP intermediate problems are those problems which have exponential solution, which have exponential time complexity. So the time complexity is actually exponential for the graph isomorphism. So if you want to prove that two graphs are isomorphic, if you want to prove this, then this problem is very hard. Not simple hard. This is extremely hard. This is NP intermediate, means this has exponential time complexity. But if you want to show that graphs are not isomorphic, showing not isomorphic is easy. Showing not isomorphic is actually easy. Not isomorphic can be done very easily. That two graphs are not isomorphic, okay, can be done using something called graph invariants. Using graph invariants, there is something called graph invariants. What are graph invariants? These graph invariants, these are basically the properties. These graph invariants are basically the properties of graph which isomorphic graphs should have. See, remember, these are the graph invariants. So showing that two graphs are not isomorphic, that can be done using graph invariants. These graph invariants are properties which isomorphic graphs should have, like properties which should be same in isomorphic graphs. In isomorphic graphs, these properties must be same. Are you getting what I'm saying? Can anyone tell me which properties must be same in two isomorphic graph? Graph invariants. Which properties? Graph invariants. Remember, these graph invariants, these are the properties. These are the properties which should be same, which should be exactly same in isomorphic graph. If I give you two isomorphic graph, then what should be same? Number of vertices must be same, yes or no? So the order of graph must be same. Number of vertices must be same. Number of edges must be same. Okay, so means number of vertices must be same. Number of edges must be same. What else? Degree sequence must be same. Degree sequence must be same. And what else? For example, I can say maximum degree must be same. Minimum degree must be same. Okay, maximum degree, minimum degree, they must be same. What else? Number of three length cycles must be same. Number of three length cycles must be same. Number of k length cycle must be same, like 4 length, 5 length. Number of k length cycles must be same. Yes or no? So these properties, if you notice, these are the graph invariants. Means these are the properties which should be same for isomorphic graph. If you have two isomorphic graph, then these properties must be same for two isomorphic graphs. Maximum degree, minimum degree, okay, order of a graph, size of a graph, degree sequence, all these things. Number of cycles. What else? Diameter. What else? Diameter. What else? Connected. What else? Connectedness. Means either they both must be connected or they both must be disconnected. So connectedness. So these concepts, all these concepts, they are basically graph invariants. Is this clear? Is this clear to everyone? One more thing. If all these things are same for two graphs, can I say they are isomorphic? If all these things are same for two graphs, can I say they are isomorphic? No, you cannot say. Remember. If any of these property is different for two graphs, then you can say they are not isomorphic. But if all these properties are same for two graphs, it does not mean that they are isomorphic. Okay, so this is the point. This is the note that, okay, if some graph invariant, there is, like, if at least one graph invariant is different, at least one graph invariant is not the same for two graph, then what can I say? Is not same for two graph. If some graph invariant, these graph invariants, these are the graph invariants, these are the properties. Remember, these are the properties which should be same for isomorphic graph. If some graph invariant is not same for two graph, then they are not isomorphic. Then they are not isomorphic. But remember, if all properties are same, if these, okay, these previous, if previous all graph invariants are same, if previous all graph invariants, remember, all graph invariants are same for two graph, then it does not mean they are isomorphic. Then it does not imply, then it does not mean, remember, it does not mean they are isomorphic. Okay, is it clear to everyone? So these properties are necessary but not sufficient. These properties, all these properties on your screen, all these properties are necessary, but they are not sufficient. These properties, these graph invariants, these are necessary but not sufficient. They must be same for isomorphism, but they are not sufficient. Again, I am telling you, graph isomorphism is an NP hard problem, like NP intermediate problem. Graph isomorphism is very hard problem. Okay, so these are one way. If these are one way, so this is what I'm saying. If some graph invariant is not satisfied, then not isomorphic. But if all graph invariant are satisfied, it does not mean they are isomorphic. It does not mean they are isomorphic. So all these properties, these are necessary but not sufficient. So please understand this. So we have seen the definition of isomorphism. This is the definition of isomorphism. And then we have seen, tell me, okay, let's check. Are these two graphs isomorphic? Tell me, are these two graphs isomorphic? Don't apply the definition of isomorphism. Just tell me, are these two graphs isomorphic? Yes, these two graphs are isomorphic. What we have to do? Basically, you pick this V3 and you pull this away. What you do? These are isomorphic because you take this V3, and you untwist this. You take this V3. Basically, this is twisted. I can say this is G, this is twisted G. Actually, they are same because what you can do, you can this V3 you can pick and you can pull it here. Okay, you can untwist. Are these two same? These two graphs? Yes, they are also isomorphic. This is also K4, this is also K4. Both of them are K4. This is also complete graph on 4 vertices. This is also complete graph on 4 vertices. Here also every 2 vertices are adjacent. Here also every 2 vertices are adjacent. So because they are K4, K4, so yes, they are isomorphic. What about these graphs? What about these? These two graphs. These two graphs are not isomorphic. Why? These two graphs are not isomorphic. See the maximum degree here. Here the maximum degree is 4. And here the maximum degree is what? Here the maximum degree is 3. If you notice, the maximum degree you can check. Or here you have a pendant vertex. Here you have a pendant vertex. Here there is no pendant vertex. Here we have a degree 1 vertex. Here we don't have a degree 1 vertex. Yes or no? In this H, maximum degree is 4. Okay. Similarly, in this H, if you notice in this H, the degree sequence will be what? The degree sequence is 4. This has degree 4. Then you have a degree 3. Then you have a degree 2. Then you have a degree 2. Then you have degree 1. And what is the degree sequence of G? Degree sequence of G, that is 3, 3, 2, 2, 2. So of course, degree sequence is different. So you can use these things. Because degree sequence is different, so these are not isomorphic. What about these two? Graph G, H on your screen here. What can you say? Are they isomorphic? Why they are not isomorphic? They are not isomorphic. What is the reason? What is the reason? See, maximum degree is same. If you notice, both of these graphs have the same maximum degree is same. Actually, the degree sequence is also same. Degree sequence is also same. Number of vertices is also same. Number of edges is also same. Degree sequence is also same. So what is different? So what is different? 4 length cycles. Let's find out how many 4 length cycles we have here. In this G, how many number of 4 length cycles? What is that? What will be the number of 4 length cycles? So here number of 4 length cycles, if you notice, this is a 4 length cycle 1. This is another 4 length cycle 2. Do we have another 4 length cycles? Like, is there any other 4 length cycle? In this G, we have only 2 4 length cycles. See, this is a 4 length cycle. This is a 4 length cycle. If you notice, there is no other 4 length cycle. These are actually not 4 vertices. These are not 4 vertices. So you should have 4 vertices. Can you create any other 4 length cycle? So in H, how many 4 length cycles you have? How many 4 length cycles? How many 4 length cycles you have? So number of 4 length cycles, that will be, this is a 4 length cycle. This is a 4 length cycle. This is a 4 length cycle. Basically, that is greater than equal to 2. I can say that is 3. Okay, so the number of 4 length cycles, so they are not isomorphic because the number of 4 length cycles is different. You can notice here, number of vertices same, number of edges same, degree sequence same, diameter same, maximum degree same, minimum degree same. But okay, this number of 4 length cycles, that is different. So I can say these are not isomorphic. Is it clear to everyone? Please tell me. So remember, let me just tell you. Now you can notice what is a graph invariant. The definition of graph invariant. Graph invariant means it does not vary. Invariant means it does not change for isomorphic graphs. If you have two isomorphic graph, then it does not vary. It does not change. Graph invariant is a property of graph that is preserved by isomorphism. If two graphs are isomorphic, then they must have same invariants. Okay, this G1 has some invariant property, then G2 also should have same invariant property. Common examples of invariant like number of edges, number of vertices, degree of a vertex, and there are many others. Like these are the invariants. Isomorphic invariant, what it means? These are the properties which should be same for isomorphic graphs, like number of vertices, number of edges. Okay, for example, maximum degree, minimum degree has a vertex of degree k, has m vertices of degree k, has a circuit of length, cycle of length k. Okay, has a simple circuit. Simple circuit means cycle. Actually, some people simple circuit, that simply means cycle. Simple circuit, this is the name for cycle. So has cycle of length k, has m cycles of length k, is connected Euler, Hamiltonian, these things we will study. There are many others like coloring number. Okay, we will study in future. We will study in future. Coloring number, omega number, independent number. Okay, there are many other concepts. These concepts we will study in the futures. In future, we will study these concepts. But the point is that these concepts are also graph invariant. They must be same for two isomorphic graphs. Are these two graphs isomorphic? These two graphs, are they isomorphic? Tell me. This is not a vertex. This is not a vertex. Remember, this is not a vertex. So number of vertices is actually same. So why they are not isomorphic? They are actually not isomorphic. What is the reason they are not isomorphic? Can anyone tell me? Four length cycle. Okay. So here you have a four length cycle. Here we have a four length cycle. Do we have four length cycle here? Can you create a four length cycle here? Like, can I create a four length cycle here? Can I create four length cycle? Yes, this is a four length cycle, right? You can go from here to here. You can go from here to here, here to here, here to here. So this is a four length cycle. What about five length cycle? Okay. So four length cycle is not a problem. Four length cycle is not a problem. What about five length cycle? Here we have a five length cycle. Okay. Like what you can do, you can create a five length cycle like this. These vertices, if you take, then you will get a five length cycle. Okay. Here, can we create a five length cycle? Tell me, in this graph, do we have a five length cycle? Five length cycle do we have? In this graph, can you create a five length cycle? I think in this graph, there is no five length cycle, right? In this graph, if you check, please check this. There is no five length cycle in this graph. And there is five length cycle. There exists five length cycle. You can also check maybe like number of vertices is same, number of edges is same, degree sequence, if you check, that is also same, degree sequence is also same. And what about diameter? What about diameter? Like, what is the diameter? For example, if you notice, from any vertex to any vertex, from this vertex, if I want to go, then 1, 2, I think, okay, you can check. Basically, actually, this five length cycle, I think this will work, because here there is no five length cycle, and here you have a five length cycle. So these are not isomorphic. Okay. Next, what about these two? Are they isomorphic or not? These two graphs, are they isomorphic? These two, check them. Are they isomorphic? These are actually not isomorphic. And what is the reason? The reason is actually very simple. Because if you notice, I think you have a, here you have a degree 4 vertex. You have a degree 4 vertex. Here also you have degree 4 vertex, but here you have 2 degree 4 vertex. Here also you have 2 degree 4 vertex. This is degree 4. This is degree 4. Okay, so the degree sequence, I think the degree sequence will work here. For this question, the degree sequence will actually work. This is the degree sequence here, and this is the degree sequence here. So this, there is no vertex of 3 degree here. There is no vertex of degree 3 in this graph. So the degree sequence will actually work. Okay, so they are different because their degree sequence is different. Very simple. What about these? This is your GATE exam question. What about these? Avni, there is no formula for this. Avni, see, graph isomorphism is a very hard problem. Graph isomorphism is not easy. Please understand. There is no theorem for graph isomorphism. There is only a definition, but if you apply the definition, it will take a lot of time. If you apply the definition, then you will only solve one question in the exam. If you apply the definition, only one question you will solve, and that also maybe you will not be able to solve. So remember, graph isomorphism is not easy. There is no process, there is no procedure. You have to check all these properties that I told you. Avni, you have to check all these properties that I told you one by one. Start from number of vertices. See, always start from number of vertices, then you check number of edges, then you check degree sequence, then you check maximum degree, then you like, okay, so first of all, this is the order you should do. This is the order you should apply to, okay, the order of invariants to check, order of graph invariants to check. What is the order of graph invariants to check? So you should check in this order. You should start with number of vertices, then you should check number of edges, then you should check connectedness, are they connected or not, then you should check connectedness, then you should check degree sequence. Okay, then you should then after that, if you check degree sequence, you don't have to check maximum degree, minimum degree, you don't have to check that. Okay, so you just check degree sequence, then you check number of 3 length cycles, number of 3 length cycles, you check cycles, then you check number of 4 length cycles. Okay, then you check number of 4 length cycles, then maybe you can check number of 5 length cycles, something like that. Okay, so basically I think this will be enough. Whatever gate question they give you, I think these will be enough. These things you can check. Also, if you want, if diameter, if checking diameter is easy, then you can check diameter also, but finding diameter is not easy. You can check diameter also. Now let's see this one, this question. This is your gate exam question. So in this question, first you, okay, let's check. So first you directly check like 1 1, this has 2, this is degree 4, 2 2 2 2, this is the degree sequence. Okay, now here, first of all, you can notice you have a triangle. You have a triangle here. So this option is incorrect. You have a triangle. There is no triangle here. There is no 3 length cycle here. You don't have any 3 length cycle. Also, there is no 4 length cycle. There is no 4 length cycle. We don't have any 4 length cycle. But here you have a, I think, okay, so here we don't have a 4 length cycle. But here you have a 4 length cycle. Here you have a 4 length cycle. So this is gone. Next, what about the next? Only 2 options are remaining. Only 2 options. Here you can notice that this vertex has degree 3. So this option is also gone. So the answer will be B. Yes or no? Because this vertex has degree 3. So this option is also gone. And there is no cycle of length 4. There is no cycle of length 3. So finally answer will be option B. That's it. What about this? Yes, these are all isomorphic to each other. You can check. All of them are isomorphic to each other. So this is the order of graph invariants to check. Is this clear? The graph isomorphism concept. Please tell me, is this concept clear? Graph isomorphism. Graph isomorphism is not easy to check, but these things you can apply. Remember one thing, always remember one thing. If all the graph invariants are satisfied, it does not mean they are isomorphic. To say that 2 graphs are isomorphic, it is not easy. But if some property is not satisfied, then you can say they are not isomorphic. So please remember this point. Okay. Is this clear? So this is the idea. Now let's solve this question. What is the answer for this? True or false? So remember, if you notice, this is a nice question. I found this in a university. So this is saying that let A be the set of all graph, be the set of all simple graph on n vertices. So remember, in this A you have graphs. In this you have all the simple graphs. in this you have all the simple graphs. Okay. Now, for example, all the simple graphs you have, for example, your K3, your K4, your W3, your C3. Okay. Like this, you have all the graphs you have. All the graphs we have, for example, Q4, sorry, Q2, and so on. So all the graphs you have. Now, what this is saying? We are defining a relation on A. So we are defining a relation on A. What it means? Relation on A. What it means? It means we are relating the elements of A to elements of A. It means graphs are related to each other. Graphs are related to each other, and we are saying that two graphs are related to each other. Basically, this is the definition of isomorphism. Can you notice? Two graphs are related to each other. Two graphs are related to each other. If you notice, please notice this. This is the definition of isomorphism. There exists a bijection between the vertices such that UV is an edge if and only if FUFV is an edge in G dash. This is the definition of isomorphism. So we define a relation R on A such that this G1 is related to G2 if and only if G1, G2 are isomorphic, because this is the definition of isomorphism. Now the question is asking, can I say true or false? This equivalence relation, this R is equivalence relation. Did you understand the question? The set is a set of simple graph. So you have a set. In this set, you have graph G1, G2, all the simple graphs you have in this set. Now we are defining a relation R on this set. It means that these graphs are related to each other. These graphs, they are related to each other. G1 is related to G2 if and only if G1 and G2 are isomorphic, because this is the definition of isomorphism. If you notice, this is the definition. So finally, now tell me, are they can I say graph isomorphism is equivalence? Graph isomorphism, can I say this graph isomorphism, if you notice, this is reflexive? Can I say this is reflexive? Yes, this is reflexive, because every graph is isomorphic to itself. Every graph is isomorphic to itself. Can I say this is symmetric? Yes, this is symmetric. If G is isomorphic to H, then H is isomorphic to G. And can I say this is transitive? Can I say this is transitive? Yes. If G is isomorphic to H, H is isomorphic to P, then I can say that G is isomorphic to P. So this graph isomorphism is an equivalence relation. This is an equivalence relation. So in this question, you can notice the definition of graph isomorphism is given. This is a standard university question. I think this is from Washington University. This is a question from Washington University. And you can notice in the GATE exam, they can ask you this type of questions, because in the GATE exam, they will not mention the word isomorphism. This word isomorphism, they will not mention. They will directly give you the definition of isomorphism. The definition of isomorphism, they will give you directly. So that is the reason the definition is important to understand, but we will not apply the definition in our questions. In our questions, we will only apply the methods that we have seen. Basically, if I give you two graphs, what you have to do, you have to see only small graph will be given to you. Remember, in the GATE exam, they will not give you big graph. They will not give you. Only small graph they will give you, because the graph isomorphism is not an easy task. So that is the reason only small graph will be given. And when small graph is given to you, then you can check these things: number of vertices, number of edges, degree sequence, okay, like all these things, number of 3-length cycle, number of 4-length cycle, these things you can check. If any of them mismatch, then the graph are not isomorphic. If all of them match, then please tell me, if all of them match, then actually we cannot say anything. But the graph that will be given to you, that will be small graph, remember. So when a small graph is given to you, you can check like by twisting. Maybe you can twist. Okay, sometimes you can twist, and sometimes you can check whether this is K4, K5, W3, W4, what is this? So basically like that you can check. Okay. So this is your graph. Okay. So this was your graph isomorphism. I hope this topic is clear. Now let's see the next topic, that is complement of a graph. What is this? This is very simple. Complement of a graph. Can anyone tell me every graph is subset of subgraph of what? Tell me. I want to find complement of a graph. I want to find this. If you notice every graph on n vertices, if you notice every graph on n vertices, that is subgraph of what? Every graph, whatever graph you take on n vertices is a subgraph of what? Is a subgraph of kn, is a subgraph of complete graph on n vertices, correct? Yes. So every graph, whatever graph you take on n vertices is a subgraph of kn. So for every graph, this kn is working as what? This kn is working as a universal set. For every graph on n vertices, this kn is working as a universal set. So I can say what is G complement? G complement will be, okay, remember G complement will have the same vertices. If you have a G which is V comma E, then G complement will have same vertices. Vertices will be same, but edges will complement. So when you complement the graph, then vertices are same, but only edges will complement. And what are the edges? The edges will be the edges in Kn minus the edges in E. Okay, so this will be the idea. Basically, it means that G complement means vertices will be same. Vertices will be same, but those edges which are in G, you remove those, and those edges which are not in G, you put those. So just do the complement of edges. This is what you have to do. Only you have to do complement of edges, means E bar, that is nothing but all the edges minus these edges, all the edges minus these edges. Is it clear to everyone? Very simple. So for example, if you want to find the, like for example, if I give you this graph, if I give you this graph, then what is the G complement? Tell me what will be the vertices will be same. The vertices will be same, but the edges will complement. The edges will complement. Very simple. The vertices will be same. So tell me what is the complement of K4? For K4, what is the complement? Complement of K4 will be E4, right? That will be E4. Edgeless graph on n vertices. This is edgeless. Yes or no? If you want to find K4, K4 means complete graph. So the complement of complete graph will be E4, isolated graph. Yes or no? So like this. So very simple. So I can say Kn complement is what? Kn complement is En. This is the idea. Okay. So very simple. The concept of this complement is actually very simple. Whatever graph I give you, for example, 1, 2, 3, 4. If I give you this graph, then if I give you this graph, then what is G complement? The vertices will be same. There is no change. Vertices will be same, but edges will complement. See, this edge is not in G, so you will put this edge. This edge is not in G, so you will put this edge. So this G complement will be like this. That is disconnected. This is disconnected. 1 related to 4, 2 related to, so 1 and 4, they are adjacent. 2, 3, they are adjacent. This is the definition of complement. This is how you can find the complement of graph. So vertices will be same, but edges will complement. Very simple. Okay, now tell me. So this is my question. Let's do the analysis. Let's do the analysis. So if you have G and you have G complement, in G you have vertices. Let's assume you have vertices V1 and let's assume you have edges E1. And in G complement you have vertices V2 and you have edges E2. Then first thing, what can you say about number of vertices? See, V1 will be exactly same as V2. Yes or no? The vertices will be exactly same. All the vertices here, they will be same as all the vertices here. So V1 and V2, they are exactly same. But you can notice E1 is basically, I can say E1 complement. E2 is basically E1 complement. E2 is basically E1 complement. Okay, so tell me what is the number of edges? Like what can I say about number of edges in G bar? What is the number of edges? That will be total number of edges. That will be total number of edges. So first you find out what is the total number of edges. So the total number of edges is NC2. minus number of edges in this. Okay, because we are okay, so total number of edges, that is NC2, minus number of edges in this, because we are doing the complement of edges. We will do the complement of edges. Okay, so I can say number of edges in E1 plus number of edges in E2. What is that? That is equal to NC2. The total number of edges, that will be NC2. And this is the number of edges in Kn. Basically, this is the number of edges in Kn in complete graph of n vertices. So very simple. Now, what is a self-complementary graph? The definition of self-complementary, the name itself is telling you what that means. Self-complementary means the complement is same as itself. So what is the definition of self-complementary? Self-complementary graph means G is isomorphic to G complement. They must be isomorphic. They must be isomorphic. Need not exactly same. They must be isomorphic. If they are isomorphic to each other, then we will say that they are self-complementary. G is isomorphic to G bar. So tell me, is this graph isomorphic? Is this graph self-complementary? A, B, C. Can I say this graph is self-complementary? Can I say this graph is self-complementary? What will be G bar? G bar will be like this. Are they isomorphic? Are they isomorphic? These two are not isomorphic. So this G is not self-complementary. This is not, so I can say this is self-complementary graph. So this is not a self-complementary graph. This graph is not self-complementary. So very simple. Can anyone give me a self-complementary graph? Like I can give you this A, B, C, D. Consider this graph. Is this self-complementary? This graph G. So what will be G bar? A, B, C, D. G bar will be like this. G bar will be like this. Are they self-complementary? Yes, they are actually isomorphic. These two are actually isomorphic. Yes or no? They are isomorphic to each other. This graph and this graph, they are isomorphic to each other. So I can say this G is self-complementary. This is a self-complementary because they are isomorphic to each other. Remember, this G and G bar, you can clearly see they are isomorphic. This is twist. So this is same as what you can do. You can untwist this. You can just untwist. So you can notice they are actually isomorphic. So they are self-complementary. Yes or no? Are Arpan, this is a very small graph. This is very small graph, very small graph. You can simply untwist this. Just untwist. If you untwist, then you will get this. Just untwist. Very simple. You don't even have to do anything. Just untwist. Then you can notice, yes, they are actually same. This is a very simple graph. So this is the idea. Remember, G is self-complementary. This is the definition. Please see the definition. If you understand definition, automatically you are gate, like you have cracked gate exam. Just understand the definition. G and G bar, they must be isomorphic. For example, this is G bar, and you can notice they are isomorphic. So I can say G is self-complementary. This graph G is self-complementary. Okay. So any graph is self-complementary if G is isomorphic to its complement. This is an interesting question. A cycle on n vertices is isomorphic to its complement. A cycle on n vertices is isomorphic to its complement, the value of n. A cycle on n vertices. What you will do? So this is basically your Cn, and this is saying that this Cn is isomorphic to its complement. This Cn is isomorphic to its complement. What it means? If two graphs are isomorphic, then their number of edges will be same. Can I say their number of edges will be same if two graphs are isomorphic? Yes or no? Two graphs are isomorphic, so their number of edges will be same. Definitely their number of edges will be same. What is the number of edges in Cn? So what is the number of edges in Cn? In Cn, how many edges you have? N edges. In Cn, we have n edges. So what is the number of edges in Cn bar? What is the number of edges in Cn bar? That is nc2 minus n. That will be nc2 minus n. Just put them equal. put them equal. So from here you will get 2n is equal to n minus 1 by 2. And so from here you will get 4n is equal to n square minus n. So n square is equal to 5n. And so n is equal to 5. So n is equal to 5. So the answer will be n equal to 5. Basically, C5 is isomorphic to its complement. The question is saying that a cycle is isomorphic to its complement. Means this Cn is isomorphic to Cn complement. Okay. If two graphs are isomorphic, their edges will be same. Number of edges in Cn, that will be n. And you can notice if you have n edges here, then number of edges in Cn complement, that will be nc2 minus n. This will be the number of edges in Cn complement. So now you can put them equal. Just put them equal. So you will get n equal to 5. So basically C5, if you create, for example, if you create C5, this is your C5, A, B, C, D, E, this is your C5. Tell me what is C5 complement. Please create the C5 complement. So if you create C5 complement, A, B, E, C, D, if you create the C5 complement, that will be like this. This will be the C5 complement. Okay, so right. So this will be the C5 complement. Actually, they are isomorphic. You can check. These two are isomorphic. How to make sure they are isomorphic? Tell me what you will do to make sure they are isomorphic. Twist. Just pick this and pull this here. Okay, just pick this and pull this here. So what you can do? You can pull this on this side. Just pull this on this side. So if you pull this on this side, then what will happen? See what will happen. If you pull this E here, if I pull this E here, then what will happen? These edges are now these edges you can put here. Okay, so this edge you can put here. Right. Okay, so you can basically this E you can put here. Maybe you can put this E here. So something like this will happen. Now what you do? This C also you pick. This C you put here. This C, what you do? This C you put here. So you can put this C here. Is some edge is missing? 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5. Something is wrong. Right. Okay, so actually, if you, yeah, sorry, EC, that is actually EC. Okay. Sorry, that is basically EC. If you notice, that is basically EC. E should be, E is connected to C. You can notice, see, E is adjacent to B comma C. This B is, this C is connected to D. Sorry, this C is not connected to D. This C is actually connected to A, and this D is actually connected to like this. So something, this D is connected to B. Anyway, so if you notice, this is actually same. Okay, if you just make the changes, then they will be actually same. Or maybe you can put this one. Maybe you can put this D here. You can put this D. Okay, so now you can notice they are actually same. Okay, yes or no? So they are isomorphic. So this C5 and C5 complement, they are actually isomorphic. So this C5 is self-complementary. I can say this C5, this is a self-complementary. This E5 is self-complementary. So remember, these two graphs are actually isomorphic. And this is a popular question actually. This is this is a standard question. They can give you this standard shape. This type of shape they will give you. Okay, they can give you this type of shape. Like here we got this shape. So this star type of shape they can give. This, and then something like this. They can give you this type of shape. They can give something like this. Okay, and this vertex is connected to these two. Okay, whatever actually. So let me write like this: A, B, C, D, E. So this type of shape they can give. They can give this shape, then they can connect this, then they connect with this. So this is connected to two, this is connected to, okay, so yeah. So this shape, these two shape are actually same. Okay. Anyway, now let's move on. So did you understand this? This complement of a graph. Complement of a graph is very simple, but remember this point, that if your graph is self-complementary, then few more things. Tell me, if you have a self-complementary graph, then what will be the number of vertices? What can you say about number of edges or number of vertices? If you have a self-complementary graph, if you have a self-complementary graph, then remember, it simply means that G is isomorphic to G complement. In this G, number of edges is E. Okay, so that should be equal to number of edges here. So that should be equal to number of edges here. So this is the number of edges in this, and this should be equal to NC2 minus E. So from here 2 is equal to NC2. From here 2 is equal to NC2. From here I can say N into N minus 1 by 2 is equal to 2E. Okay, so from this I can say, so for self-complementary graph, this equation you can create. Remember, this equation you can create for self-complementary graph. This will happen for self-complementary graph. That E, number of edges, will be equal to this. Now, one interesting thing you can notice here. See, N into N minus 1, that is equal to 4 into E. That is equal to 4 into E. Are they co-prime? Please tell me, are they co-prime? Are they co-prime? So yes, they are co-prime. Okay, so I can say that this number is multiple of 4. Correct? This number is multiple of 4. So this N into N minus 1, because you cannot, this number, this is multiple of 4. Or I can say like this, that, correct? Yes or no? This number is multiple of 4. Now, this number is a multiple of 4. And you can notice N and N minus 1, they are always co-prime. They are always co-prime. So this theorem we have that, if you have, basically, if A divides BC, where these are co-prime, if A divides BC where these are co-prime, then it means A divides B or C. These are consecutive numbers. Consecutive numbers are always co-prime. Saurabh, these are consecutive numbers, n comma n minus 1. For example, 4 comma 5, these are co-prime. For example, 6 comma 7, these are co-prime. 10 comma 11, these are co-prime. 12 comma 13, these are co-prime. The consecutive numbers are always co-prime. Consecutive numbers are always co-prime. Yes or no? Remember this. This we already know. These are very basic things. Consecutive numbers are always co-prime. Consecutive integers are always co-prime. They are always co-prime because their GCD is 1. If you have two consecutive numbers like a comma a plus 1, if you have two consecutive number, then their GCD will be equal to 1. Their greatest common factor will be equal to 1. Okay, and this is the theorem that if A divides BC, B into C, where both are co-prime to each other, these BC are co-prime to each other, then A divides B or A divides C. Then A divides B or A divides C. So I can say that this 4 divides n into n minus 1, and they are co-prime. So what I can say either 4, either n. So what can I say? I can say either 4 divides n or 4 divides n minus 1. Yes or no? Is this clear? See, we have a self-complementary graph. In a self-complementary graph, G is isomorphic to G bar. Because they are isomorphic, so number of edges must be same. So if you have E edges here, then we will have NC2 minus E. These many edges in G bar, they must be same. So from this, what you got? You got that n into n minus 1 is equal to 4e. These are two consecutive numbers. This number and this number, n comma n minus 1. This number, they are consecutive. Consecutive numbers are always co-prime. So n comma n minus 1, they are co-prime of, okay, they are co-prime. And this number is multiple of 4 because this is equal to 4e. It means this number is multiple of 4. Or I can say this number is divisible by 4. You can divide this number by 4. You can notice here, this number, if I put this 2 here, if I put this 2 here, then you can notice this number is divisible by 4. Okay. So because this number is divisible by 4, so I can say, and these are co-prime. This number is this number, they are co-prime. So I can say that 4 divides n or 4 divides n minus 1. So this will always happen for self-complementary graph. If you have a self-complementary graph, then 4 will divide n or 4 will divide n minus 1. This will always happen. 4 will divide n or 4 will divide n minus 1. For example, you can notice this C5 is self-complementary. In this C5, n is equal to 5. This C5 is self-complementary. So 4 divides 5 or 4 divides 5 minus 1. And you know this is correct. You know this is correct. 4 divides 4. Okay. Is this clear? Now, the last topic for this lecture, that is connected components. What is this? Components in a graph. Components are like islands. Let me tell you. What is a component? Component is like an island. If you want to understand component, then you should understand island. So component is similar to island. Okay, so tell me, if you like, okay, let's assume there is a water, and let's assume this is, okay, these are some things you have. Then tell me, how many islands are there? How many islands? So total 3 islands you have. Total 3 islands you have. Now tell me, how many islands are there? Now tell me how many islands are there? Number of islands. So let's assume this black is the water. This black is the water, means this basically you have a black water. So let's assume this black is the water. This black is the water, remember. This black is the water. So tell me how many islands you have now? Now how many islands you have? Again 3. Okay, tell me, if this is island, can I say this is also island? Like, can I say this is island? Will I say this is island? This is not island. The whole thing is island. This is not island. This whole thing is island. You cannot say that this city is island. For example, let's assume this is West Indies. Let's assume this is West Indies. So you can check the map. I think West Indies is island. This West Indies, this is an island. But you cannot say that this city. Can anyone suggest one city in West Indies? Okay. Anyway, basically you cannot say that this is an island. Barbados, yeah, Caribbean. So basically this is not an island. What I'm saying. Are you understanding this point? So island, can I say what is island? Finally, what I want to say. Island is a maximal piece of land surrounded by water. This is important. Maximal piece of land surrounded by water. Piece of land surrounded by water. Something like this. Yes or no? So for example, this is also island. This is small island. This is big. This is also big. But that is fine. This is also a small island. So I can say that's the maximal, not maximum. Not maximum. Because this is maximum. This is maximal. Maximal piece of, for example, this is not island. What is the reason? This is not island because this is not maximal. You have to take the entire thing. You have to take the entire thing. So component is like that. For example, if I give you a graph, let's assume this graph you have. Okay. So you have this graph A, B, C, D, E, F. How many components are there? Like consider this graph. How many components we have? So number of components. Number of components. So there are total 3 components in this graph. In this graph, we have total 3 components. Can I say this is a component? Tell me, can I say this is a component? Please tell me, can I say this is a component? This is not a component. This is not a component because this whole thing is component. So component is always a maximal subgraph. Can I say what is a component? Component, what is the component definition? This is a maximal connected subgraph. Maximal connected subgraph. Maximal connected subgraph. So you can notice this is maximal connected subgraph. This is not a maximal connected subgraph. Yes or no? This is not a maximal connected subgraph. This is maximal connected subgraph. So this is a maximal connected subgraph. This is the definition of component. Like island. Island is basically a maximum piece of land which is surrounded by water. So similar to that. Very simple. Yes or no? It does not matter. This is your island. For example, okay, just consider this island. This city and this city are here. They are not adjacent. This city, they are not adjacent. Still, this whole thing is island. This whole thing is island. In this island, you can have cities, small city, big city. You can have cities. This whole thing is island. Maximal. What is the meaning of maximal? Maximal means you can add something and it still will be connected. Maximal connected, what it means? Maximal connected, what it means? Maximal connected, it means that you can add, you cannot add something more. Okay, maximal connected means you cannot add something more. You cannot add something more. Keeping it connected. Maximal connected. If it is already maximal, then you cannot add something more, keeping it connected. For example, can I add something more here? For this C, D. For this C, D, can I add something more? Yes, you can add A, you can add B. It is still connected. This whole thing is a connected, right? Similarly, this whole thing is connected. Similarly, this whole thing is connected. So, okay, for this is connected. Can you add something? Like, can I add this? Now this is not connected. Yes or no? See, please read the definition. Maximal. If it is already maximal, then you cannot add something, keeping it connected. If I add this, then it is not connected. Yes or no? If I add this, then it is not connected. Avni, if I with G, if I add E, is it connected now? Please look at this. Is it connected? Only look at E, G. Are they connected? They are not connected. Are they connected? They are not connected. So that is the reason. In this G, can you add something, keeping it connected? Tell me, in this G, can you add some more vertex? Can you add some more vertex, keeping it connected? For example, can I add this vertex? No. Now this is not connected. This is not connected. This is not connected. Are Manideep, you have to focus on this graph. New graph you don't have to create. Please don't create a new graph. This graph you focus. I am saying that G is connected. I am saying G is connected. Can you add something new to this set? This set is connected. You know this set is connected. This set is connected. Can you add something new to this set, keeping it connected? Can you add something more, keeping it connected? For example, can I say D, G is connected? Can I say D, G is connected? No, they are not connected. But notice, can I say C, D? Can I say this is connected? Can I say this is connected? C, D. Only focus on C, D. Can I say this is connected? Yes. But this is not maximal. This is connected but not maximal. This is connected but not maximal. Why? Because you can add something. Because what you can do C, D, A, B. You can add this. Now you can notice this is also connected. So it means this is not maximal. You can add something. Yes or no? You can add something. Agree or not? For example, there is a child. This child says, I am full. There is a child, and this child says, I am full. If he says, I am full, then can you add something more to his tummy? If this child says, I am full, can you add something more to his tummy? Now, don't say that add one more tummy. Some students are saying add one more tummy. Some students are saying add one more age. This child is saying, I am full. Can you add some more? Can you add some more food? Can you add some more food? You cannot add some more food. But some students are saying add one more tummy, two more tummy you add. Now is it clear? Don't add extra tummy. Is this clear now? This is your graph. Don't change this graph. Don't change this graph. This is your graph. Don't change anything. Just think about it and tell me B, D, are they connected? Okay, just see B, D, are they connected? B, D. Are B, D are connected by a path. B, D are already connected. I am not saying adjacent. Please, connected and adjacent. Please see the difference between connected and adjacent. Connected versus adjacent. Please notice the difference here. I am saying connected and adjacent. Adjacent are like this, and connected are like this. There is a path. Connected means there is a path, and adjacent means there is edge. This is the difference of connected and adjacent. So I am asking B, D. Can I say this is connected? Yes, they are connected. Yes, they are connected. But can I say they are max? Can I say this set is maximally connected? Can I say this set is maximally connected? No. You can put A, C. You can put something else. You can put something else. For example, another example you can notice in our India, roadways bus is never maximally full. Yes or no? Roadways bus is never maximally full, because the conductor can always add something new. Conductor will always add something new. Conductor will say, it is okay, khali padi hai, aa jao. You know, okay, it does not matter. It does not matter how many people are already there. Khali padi hai. अरे सीट ही सीट है, आगे जाके खाली हो जाएगी. So anyway, so forget about it. Anyway, what I'm saying, please, that is the reason I'm giving you this example, island example. This island example I gave you. Why I gave you this island example? For example, this is an island. This whole thing is island. Please don't say that this is island. Okay. So this whole thing is island. This whole thing is called island. This small part is not island. You cannot say that this is island. This is not island. Similarly, this is not island. So this is the same idea. Here, this is a component. Here, this is a component. Here, this is a component. So number of components is 3. Is this clear now? Number of component is 3, because component means just select the maximal you can select. Okay. Select the maximal you can select. Select the maximal you can select, but it should be connected. Select the maximal you can select. For example, the maximal I can select is this. The maximal I can select is this. The maximal I can select is this. But if I do this, can I select like this? Tell me. Can I select like this? No, they are not connected. Can I select like this? They are not connected. Can I select like this? Yes, this is connected. Yes, this is connected, but this is not maximal. Yes, this is connected, but this is not maximal. This is connected and maximal. This is not connected. This is not connected. This is connected and maximal. This is connected but not maximal. This is connected and maximal. Now is it clear? So please tell me, this is clear, the definition of connected components, or I can say simply component. So what is a component, connected component? In this graph, In this graph G1, how many components you have in this graph G1? In this graph G1, how many components in G1? Okay, so in this G1, number of components is 1. In this G2, how many components you have? Number of components is 2. This is a component. This is a component. So number of components is 2. Remember, number of components is 2 because this is a component. This is a component. And this is a component. What about this? What about this graph H? For this H, you have 3 components. There are total 3 components. So now is it clear to everyone? The definition, is it clear? The definition. See, this is maximally connected. This is maximally connected. This is not connected. You cannot take this. This is not connected. This is maximally connected. This is connected, but this is not maximal. You can take H. You can take H. This is connected, but this is not maximal because you can take H. You can add something extra. Think like a conductor. Think like a conductor. This is not maximal because you can add one more passenger. Okay, so this is the idea. Now tell me, this is also equivalence relation, right? For example, if I give you this question, let's assume you have a graph G. You have a graph G in which you have vertices and in which you have edges. And in this graph G, let's assume number of components is equal to number of components is equal to, let's assume, Y. And on this, on V, remember on V, on this V I am defining a relation. On V I am defining a relation R. On this set V I am defining a relation R such that A is related to B if and only if they belong to same component. They A, B are in same component. Are in same component. Or I can say, tell me, when can I say they are in same component? Tell me, two things are in the same component. What it means? Two things are in same component. What it means? Please tell me. Two things are in same component. What it means? You have a graph G, V, E, and I am saying A, B belonging to V. I am saying that A, B belong to same component. Belong to same component. If and only if belong to same component, if and only if they belong to same component, if and only if there is a path. There is path between them. If and only if there is a path between them. There is a path between A, B. Means between A, B, there is a path. And if there is a path, then they are in the same component. Agree or not? This is if and only if. Because if there is a path between them, then it means they are in the same component. Similarly, if they are in the different component, what it means? They are in different component. What that means? They are in different component. It means there is no path between them. There is no path between them. If and only if there is no path between them, there is no path. There is no such path, basically. So this is the idea. Now, this is the definition. This is the question. You have a graph. In that graph, you have number of components is Y. On V, on this set V, set of vertices, I am defining a relation R. I am saying that A is related to B if and only if A, B, if and only if there is a path between A, B. If and only if there exists a path between A, B. Tell me, this R is equivalence relation or not? What can you say about this? Can I say this is equivalence relation? Can I say this is equivalence relation? First you tell me this. And if this is equivalence relation, if yes, then what is the number of equivalence classes? What is the number of equivalence classes? So yes, this is equivalence relation. This is equivalence relation because you can clearly see that they are in the same component. Remember this thing, this statement means they are in the same component. There exists a path between a comma b. This means there exists a path between a comma b. It means a comma b belong to same component. So finally, I can say yes, this is equivalence relation because this is reflexive, symmetric, transitive. And you can notice number of equivalence classes will be y. Every equivalence class is a component. Yes or no? Every equivalence class is a component. Let's understand this with example. For example, consider this graph. Let me give you a graph like this: A, B, C, D, E, F, G. This is your graph. Now, in this graph, you have vertices, you have edges. So on V, you are defining a relation R on V, and we are saying that V1 is related to V2 if and only if they have a path. If and only if there exists a path. If and only if there exists a path between V1 comma V2. This is the idea. Now tell me, can I say A is related to B? Can I say A is related to B? Yes. Can I say C is related to E? Yes. Let's assume this is the graph. Can I say C is related to E? Yes. Can I say D is related to E? Tell me. Can I say D is related to E? Yes. Can I say F is related to G? No. Can I say F is related to F? Yes. Can I say G is related to G? Yes. Can I say B is related to C? No. So you can notice this is a reflexive because every element, remember this is your set. This is your base set. Your base set is set of vertices. So these vertices are your base set. So every vertex is related to itself. Also you cannot, this is symmetric, and you cannot, this is symmetric. Also this is transitive. Because why this is symmetric? So this is why this is symmetric. This is symmetric because if there is a path from A to B, then it means there is a path from B to A. Yes or no? If there is a path from A to B, then there is a path from B to A. This is transitive also. This is transitive also because if there is a path, okay, and if there is another path from, then I can definitely say there is some path from A to C. Then I can say there is some path from from this to this, and this is reflexive also. Okay, so this is symmetric, transitive, reflexive. Why this is reflexive? This is reflexive because there is a trivial path from A to A. A to A is a trivial path. That is a trivial path. Okay, path of length 0. There is a trivial path length 0. Okay, so this, finally I can say that this relation R, this is equivalence relation. This relation R is basically equivalence relation. And because this is equivalence relation, so what will happen? So R is equivalence relation. So what will happen? Your relation R is equivalence relation. So because R is equivalence relation, so who will partition? Who will partition? So your base set means set of vertices that will partition in equivalence classes. Your base set will partition in equivalence classes. Tell me, in this equivalence class of A, who will come? In this equivalence class of A, this is equivalence class of A. Who will come in this equivalence class of A? Who will come in equivalence class of A? B will come. Who will come in equivalence class of C? In equivalence class of C, C, D, E, they will come. C, D, E, they will come. Who will come in equivalence class of G? G will come. And who will come in equivalence class of F? F will come. So finally, how many equivalence classes you have? So you can notice. So total 4 equivalence classes. So there are 4 equivalence classes we have, and every equivalence class is a component. This equivalence class is a component. This equivalence class is a component. So every equivalence class is a component. Is it clear? the understanding of this question, is it clear? That so if your number of components is y, then for this question, for this equivalence relation, number of classes will be y. Yes or no? Very simple. See, very simple explanation I have given to you. I have taken this example and I've told you what this question means. This question, this relation is symmetric, transitive, reflexive. This relation, this is the base set. And because this relation R is equivalence relation, so this base set will partition. So this base set, this will partition in equivalence classes. So these are the 4 equivalence classes. This is equivalence class of A. This is equivalence class of C, equivalence class of G, equivalence class of F. So total 4 equivalence classes we have, and every equivalence class is basically a component. Okay, so this is the equivalence class. This is the equivalence class. So like this. Okay, this is another equivalence class, and this is another equivalence class. Now let's take a break. So we will start. You can take dinner. Okay, so after 1 hour we will start. Okay, take dinner. So is it fine? Let me know. So the next lecture, we will not, basically this lecture we will finish, and the lecture number 6, next lecture, lecture number 6, that will start at after 1 hour. So we will start it at 8:30. Okay. Did you understand in this class what we have seen? We have seen graph isomorphism. What is important? The isomorphism definition is important, but we will not use it. In the GATE exam, they can directly ask you the definition of isomorphism, or they can give you a question in which they will not give the word isomorphism, but they will give the definition. So that is the reason understanding the definition is important, so that you can solve some questions. Okay. Any other doubt? So, okay, so this is what I want to say. Graph isomorphism we have seen, and also we have seen complement of a graph. You know that every graph on n vertices is a subgraph of Kn. So I can say how to find complement. Vertices will be same, but you will complement the edges. Okay. Then we have a concept of self-complementary graph. Self-complementary means a graph is self-complementary if and only if G is isomorphic to its own complement. Means a graph is isomorphic to its own complement. So some graph are isomorphic, some graph are not isomorphic. Then we have seen for self-complementary graph, what is the number of edges in G? So number of edges in G will be equal to NC2 minus E. Okay, so that is the relation. That then we have seen that for any self-complementary graph, 4 will divide either number of vertices or number of vertices minus 1. So 4 divides n, or 4 divides n minus 1. So that will happen for all the isomorphic graph, for all the self-complementary graph. Then we have seen the concept of components, connected components. Okay, and so yeah, so in the connected component is like a maximal structure, maximal subgraph which is connected, maximal connected subgraph. It is like an island. Okay, so the whole thing you have to consider. So that is the idea. Then we have seen some questions related to isomorphism, and also we have seen some questions related to components and complement. Okay, any other doubt anyone has? Avni is asking, these concepts were for simple graph. Yes, all the concepts that we have seen, they are only for simple graph. Okay, the concept of the concept of walk, trail, cycle, circuit, this concept of component, the concept of isomorphism, the concept of this whatever concept like complement concept, all the concept that we have seen, these are the concept for simple graph. Most of the time, 99% of the time, all the things that we study, these are only for simple graph. In future also we will study many concepts like chromatic number, planar graph, okay, many other concepts, independent set. So many concepts we will study. Those concepts are also defined for simple graphs. Okay, so see you after 1 hour. Thank you everyone.